Earth's surface. So this will happen based upon the way how the satellite rotates the Earth's orbit. Okay, and we also discussed about the speed of the satellite. It depends upon the various applications. So with a very much the high satellites is about 22,300 miles out. Okay, so where we can able to see that when the satellite is just 100 miles, that is very nearer to the Earth. Okay, it rotates 17,500 miles per hour. Okay, whereas when we talk about on the quite far away, that is when the height is quite away from the Earth's surface, the the things that is the speed of the satellite will be very less. Okay, so this difference we have to know. Okay, so when the satellite is very nearer, okay, whether the satellite, let us say that this is your Earth, when the satellite is very nearer, it rotates very fast. When the satellite is quite far, it rotates very slow. So the period of the satellite we talk about on the one revolution is a time that elapses for the particular kind of satellite. And we also discussed that, the periods about how much the satellite can remain for one particular period. And we also discussed about on the inclination at which from the geocenter, the peripheral orbit will incline. Okay. And the angle of inclination will also says about that, so when the satellite is having a angle of inclination means the angle at which it penetrates or it provides the things that when the satellite moves from the south to north and also crosses the equator, so the orbit is ascending. Okay, so the orbit may be, that is the way we can able to say that when the satellite is going to be nearer to the Earth or far away to the Earth, it basically based upon, how the satellite is moving from south to north and how it crosses from, so this is ascending part of the orbit, ascending part, okay, where we can say that the satellite is quite nearer to the Earth's surface. Okay. When we talk about the descending part, so that is this ascending part, this is a descending part. So ascending part means it is from the south to north. Okay, and it's from the north to south. Okay, that is the south to north and the north to south will be it's a movement of the satellite. Okay, when the movement is moving from when the satellite is moving from south to north, it will be an ascending part. When the satellite is moving from north to south, it will be a descending part, decreasing part. Okay. So angle of elevation, so for an example, this is the Earth, okay, and this is going to be the Earth station, okay. We all know that Earth station is one, which is going to send your signals, and one more Earth station will be available, which is going to receive your signals. Okay. So the sending signals will go to the satellite, and the satellite will perform all the modulation, demodulation, okay, and then it will receive the signal, and it will be received by the receiving station. So this is called as a Earth station antenna. Okay, so this Earth station antenna, it has to be communicated to the satellite. Okay, so this angle is called as the angle of elevation. Okay, so this angle of elevation is called as the angle that appears between the line from the Earth station to the satellite and the line between the Earth's antenna and the Earth's horizon. This is called as Earth's horizon. That is very interesting. Okay, it's a connecting of two lines. Okay, where we can say that so the angle which connects the Earth station and the satellite, and the Earth station and the Earth's horizon. This is the horizon. So the connecting of three dots. So we call that as the angle of elevation. So if the angle of elevation is very small, for an example, let us say this angle is very small means the signals between the Earth station and the satellite have to pass through much of the Earth's atmosphere. Okay. So it will take more time, because angle of elevation will teach us, how speed your signal is moving and how fast your signal is coming back. Okay, that is called the angle of elevation. Okay, so because whenever we are having some low powers, we are using. Okay, so the high absorption of the Earth's atmosphere, so we have to minimize the time. So that is what everybody is expecting. We have to reduce the time, and rather than the signals are spending much of the time in the atmosphere. Okay, so because we know that the signals are sent from Earth's surface to the satellite, so it should not spend much of the time in the Earth's atmosphere like this. Okay. So when the angle of elevation is very less, it spends much of the time in the atmosphere in reaching our signal from here to here. So noise is also available in the atmosphere. So that is contribute to the poor performance of your signal. So whenever you're lowering the angle of radiation, the more this particular signal spends in the atmosphere. So the practical angle of elevation of the good satellite is about 5 degree. So the angle of elevation should be equal to 5 degree. So this will prevent much of the time my signal is spending the time in the atmosphere, and it will prevent the signal from the external noise. So whenever the angle of elevation is quite higher, so we can able to get the better performance. So now we are going to talk about geosynchronous orbits. Okay, so we can say that it's consisting of two words: geo, synchronous. Geo means it's called geographical. Okay, synchronous means that is an attachment. So whenever you want to use a satellite for communication, okay, so whenever a satellite is used for communication, it is called as a repeater. So the ground antenna station must be able to follow or track the satellite. Okay. So depending upon the height, we discussed how to measure the height. Depending upon the speed, we also see how the speed of the satellite. When it is the lower and when it is higher, we have discussed what is the speed. Okay. So the Earth station can able to use it only for communication purpose. So the Earth station antenna, what it has to do, it has to track the satellite from the horizon to horizon. Okay, because the satellite is moving, it's not in this position, the satellite is moving over here, so the Earth satellite will be monitor or tracks the satellite. This is the horizon, this is the horizon, and this is the horizon, and this is the horizon. So based upon the movements, okay, or we can able to track, the station can able to track it where the satellite is located. But at some point the satellite can even disappears from other side of the Earth. So at that time, when the satellite is not able to track by the Earth antenna, we cannot be able to use it for communication. Whenever you want to use the satellite for the communication, okay, if you want to use the satellite for the communication, the Earth station should continuously track the satellite. If it are not able to track the satellite, means what will happen? You cannot able to establish the communication. Sometimes it will happen, that is, the satellite will be hiding on the other side of the Earth, where our Earth station unable to track it. Okay, even though it tracks inch by inch, when it goes to the other side of the Earth, so at that time it cannot be able to support the communication. So to overcome this particular problem, because earlier when they launched the satellite, they experienced these problems. See, now we are talking and you are receiving the voice without any delay, even though there is a difference in time, there is a difference in the continent and difference in everything. Okay, you can able to hear the voice without any delay. How? Because earlier the people found out all these difficulties. The reason is, the satellite is unable to get track with the antenna. So it was going behind the communication. So my antenna has to wait, okay, until it can able to track the satellite. So they found a solution to the problem. What solution? They launched a satellite with a very long elliptical orbit so that the Earth station can see the apogee. Okay, so instead of circular path, so they is launching the satellite with a very long elliptical path. Okay, so they can the we have also seen that what is going to be apogee and perigee. So this was the apogee. Okay, this is apogee. Apogee means when the satellite is quite far away from the Earth's surface. So when it's far away from Earth's surface, where we can able to see this particular satellite can able to hiding. Okay, so that's the reason that's called apogee. So this is quite, so they made quite an elliptical path for the satellite, so the satellite can be visible to the antenna at all times. So in this way, we can able to see the satellite is always in view of the Earth station. Then only you can establish the communication. This is a very important first point. The satellite should be in the view of the Earth station, okay, for all the orbits. That only it is useful for communication for the long period. If the view is not available, we cannot able to establish the communication. Okay, so it is only during a short time where the satellite will disappear. Okay, on the other side of the Earth, that it cannot be used. Okay, so this delay we call as an intermittent. Okay, caused by these orbital characteristics is highly undesirable in various communication applications. Okay, sometimes it can able to hide on the other side of the Earth. So one way to reduce these interruptions is to use more than one satellite. Okay, so actually, typically three satellites. Okay, we have to use the three satellites. If you're using the three satellites, they're spaced in the correct orbits, can able to provide communication at all times. Not a single satellite. If a single satellite, if it unable to view the Earth antenna, the other satellite will comes into picture. So that is the reason for the continuous communication purposes, the people will place the three satellites, okay, in the orbit, okay, to perform the communication purposes to ensure the communication at all times. Because to make the communication for the continuous, we need the satellite to be visible for the Earth station at all times. So there are been multiple tracking stations and complex signal switching or hand-up systems between the stations are required. Okay. So for an example, if you're launching three satellites instead of one satellite, what will happen? You need to maintain these three satellites, and it's quite expensive, and also it is quite inconvenient also. So the cost and complexity of the multiple satellite systems, even though it is quite costly, even though it is quite complex. Okay, so the global telecommunication applications, in order to ensure the continuous communication, they went for multiple satellite systems. Okay, so for an example, we are talking about three satellites. Okay, some communication systems or organizations, they are launching even between 24 satellites to 100 satellites. To why they are using this means, they want the communication to be very fast, and there should not be any intermittent delay. Okay, so these multiple satellites, are anyway on the Earth, making continuous communication possible. Just launching only one satellite and suddenly if the communication is not established, okay, we cannot blame the single satellite what you have launched. We cannot blame the single satellite what you have launched. So in order to establish the continuous communication, the people, they were launching the multiple kind of communications. Okay, so where we can able to understand that whatever the things are needed, we have to get sure that okay, so in this particular thing. Okay. So multiple satellite systems are located in the two ranges above the Earth. Okay. So it ensures the continuous communications. So the low Earth orbiting satellites, which is referred as LEO. Okay, which is LEO means low Earth orbit. Okay, low Earth orbit means, so these satellites, so the satellites are classified into various types. One is called LEO, one is called MEO, like that. LEO satellites means they are placed in the ranges of 400 to 1,000 miles above the Earth. For example, this is the Earth. Okay, from the Earth, exactly 400 miles they will place, or 400,000. More than 1,000 to 6,000 miles, the satellites are called MEO satellites. Okay, so whenever you going the height above the Earth, okay, so whenever going above the much more height, you can able to get the better view. Okay, and you can able to have the greater coverage area on the Earth surface. So whenever you want to go for the broad coverage, okay, MEO is preferred than LEO. Okay, MEO means, it's a medium Earth orbit. Okay, because that is the reason, you are on the ground floor. Okay, on your flat, if you're ground floor, you cannot have a better view of your house. For an example, you're going to some kind of 37th floor. What will happen? You can see the complete view of the city at the 37th floor. That's what is happening. When you go for the LEO, okay, the coverage is very less. When you're going for the MEO, you can able to see the coverage, entire coverage. You can locate the satellites, you can locate the Earth stations. So whenever the higher the satellite, when you're going for much more higher, what will happen? You need much more power. Okay, power, and also that power is needed for reliable communication and then and the longer the delay. So even though we can say that the radio waves they travel at 186,400 miles per second, so there will be some kind of delay in a voice from uplink to the downlink. Some kind of delay will occur. So for MEO, the round trip delay. What is a round trip? Round trip means from the Earth station to the satellite. Okay, from satellite to the receiving station. This we call as uplink, and this we call as a downlink. This is called as a round trip. Okay, starting from Earth, coming back to the Earth, and this is called as a satellite. This is the Earth. Okay, so this particular delay for this particular round trip is about 100 milliseconds, not to the second. Okay, it's just like how you are closing your eyelid, 100 milliseconds. Whereas, the Leo, the delay is just 10 milliseconds. So the best solution is to launch a synchronous or geostationary satellite. So this geosynchronous Earth orbit. So unlike MEO or unlike Leo, there is one more satellite that is called as a geosynchronous Earth orbit. Okay, so that classification we need to know. So that's what is a MEO, what is a LEO, and what is a GEO. So in the GEO, the satellite orbits about the equator at a distance of 22,300 miles. Okay, so the satellite at this distance rotates the Earth exactly 24 hours. Okay, so the satellite, what is happening? It is rotating in synchronism with the Earth, because we know that the Earth rotates for 24 hours. Okay. Similarly, the satellite is also rotating exactly as per the Earth's. So that is the reason we call that this satellite is synchronous with the Earth. Okay. So it matches with the Earth. Okay. So as per the Earth is rotating, the satellite is also rotating. So for the one complete rotation, the Earth takes 24 hours. Similarly, the satellite is also taking 24 hours for the rotation. So we can say that the satellite is quite synchronized with the Earth. So we can able to see that there won't be that much of delay. Okay, because it follows the Earth. It follows the Earth. And it completes the rotation when the Earth also completing the rotation. So we can say that there won't be that much of delay as which what we're experiencing with the MEOs and what we're experiencing with the LEOs. Even though the delay is very less, we don't want this delay also. Okay, so for that reason, we want to it appears to be a fixed or stationary. Thus, the term synchronous or geosynchronous, or we call as a geostationary orbit. So all has the same meaning. So since the satellite remains fixed, okay, so no special Earth station tracking, especially for the geosynchronous. For the Leo and MEO, we had the Earth station and also the satellite. Okay, so this Earth station has to be tracking the satellite. Okay, whenever the satellite is moving, it has to track the entire thing. Now, what happened when you go for the geosynchronous? The satellite will be in the fixed position. Okay, the satellite will be in the fixed position. Now the Earth is rotating. Earth is rotating. Okay. So the satellite will be the fixed position. So based upon the rotation, the satellite will be fixed. That is synchronized with the rotation of the Earth. So we can say that since the satellite remains fixed, some cases, so there is no need of tracking antennas. So the antenna is justly pointly at the satellite and remains in a fixed position. So with this particular arrangement, no need to make the satellite to rotate. Okay, satellite will be fixed. Okay, and there is no need for tracking the antennas. Why we are using the tracking antennas? Tracking antennas means to track the satellite. There is no need to track the satellite because satellite is located the fixed position. Okay, at any time you are fixing at the latitude and the longitude at the one particular thing, it will be remain the same thing. But the Earth is rotating. So they found this arrangement for the geo and they made the continuous communication is possible. So most of the communication what we are using today, it's all about geosynchronous variety only. Okay, can you now understand what is the difference between the MEO, LEO, and GEO? So this is the thing. The GEO means the GEO only we are using today. That is, we are placing a satellite in a one fixed position, and the Earth is supposed to move. Okay, and this there is no tracking antennas to track that particular thing. Okay, so it will remain and it will observe the communications, and it will send the communication based upon the movement of the Earth. So we can say that approximately 40% of the Earth's surface can be seen or accessed from such a satellite. So users inside that area can use the satellite for communication. Okay, so we can say that out of 100 percentage of the Earth's surface, 40 percentage of the Earth's surface can be accessed when you're keeping a satellite in that particular area. So for the people in the Earth, for an example, in the Southeast Asia, they will have this particular satellite because it has the complete coverage of 40 percentage. For an example, the people from South America and the North America, they will have the another satellite. They will fixing that particular thing. So that satellite will be used for the access of that particular region. Okay. For an example, I'm launching a satellite for Europe. Okay. So that particular region, when I'm launching and keeping my satellite in one particular orbit, where that satellite is accessible for the coverage area of Europe means, so that satellite will be useful for the communication purpose of the Europe region. This is the reason why various countries are launching the satellite. Okay, nobody can say claim that I'm launching a satellite that has the coverage of the entire Earth because it's all a country perspective. Or some 2 to 3 countries they combine together and launch a satellite. Okay, because they find that that satellite can be able to have a coverage area of those 2 to 3 countries. So well, that's the reason, so the higher power is required for such a great distance, and round trip delay is about 260 milliseconds, which is very noticeable in voice communication. We can able to notice, but now that uh, delay is also reduced. You can see that, actually MEO 100 millisecond, LEO is 10 millisecond for the round trip, but here the round trip delay is quite higher, but it minimizes the cost of the tracking stations and it makes a fixed path of your satellite. So to use a satellite, you must be locate its position in the space. Okay. So for an example, if you are launching for Philippines, you have to locate at which position you have to launch this particular satellite. So we want to predetermine the position by the design of the satellite during this initial launch and subsequent position adjustment. So in the next class, I will tell you how to adjust the position of the satellite from the Earth's surface. So once you understand the position is known, because you should know at which place in the space the complete Philippines will be covered, okay, through this particular satellite. So the Earth station antenna can be pointed at the satellite for optimum transmission and the distribution. Transmission means, that is transmitting your voice signal. Reception means after modulating signal, you can able to get. So for geo satellites, the Earth station antenna can be adjusted once and it will remain that position except for any kind of minor adjustments. Only one time you are launching, only one time you are fixing the position. That's all. So for an example, you're going for the other satellites means, so it will be vary. Every often you have to change its positions, and every often you have to make some minor adjustments depending upon the orbital characteristics because the satellite is moving in the orbit. But in this geo, it is not moving in the orbit. It is located in one particular position. That's all. So we have to make use of some special tracking systems whenever we're going for the MEO or LEO. Okay, this tracking system is essentially an antenna. Okay, so where we can able to make the position can be changed to follow the satellite across the sky. So to maintain the optimum transmission distribution and reception, the antenna must be continuously pointed at the satellite. So the location of the satellite is generally specified, okay, in terms of latitude and longitude. Okay, that's what I already mentioned. If you're launching the Philippines, you have to know the latitude and longitude. The satellite location is specified by a point of surface, which is normally called as the sub-satellite point, SSP. So this point is located by using the conventional latitude and longitude designations. Okay, so this system is widely useful for navigational purposes. Okay, so if you have ever studied a globe of the Earth, you can see some kind of lines in the Earth that shows that latitude or longitude. Okay, so the longitude are drawn on the surface between the north to south poles like this. Okay, sorry, north to south poles. Okay, okay, that's called the longitude. Latitude means it is quite parallel to the equator. Okay, so based upon this, the center line of the latitude is going to be the equator, which separates your northern hemisphere and the southern hemisphere. So the latitude we can able to see that this is called as a latitude. Okay. So for an example, if you want to position this Washington, okay, so this Washington is positioned with a latitude of 39° north and 77° west. Okay. So we can say that the latitude is the angle between the line drawn from the given point of the surface of the Earth to the point of the geocenter. This is called as the geocenter. Okay. This is the angle of latitude. This is shown to be the equator. And this is going to be the east, and this is the west and the north, and this is called the south. And this is the angle of longitude. Okay. And this is called as a prime meridian, which connects these 2 points. Okay. So we should understand that, if you're having some interest on this geology and the geography, so where you can able to understand that, this point that connects your geocenter, and if you draw a straight line, then you can able to understand that you can able to understand which country is located over here, which is quite a straight line to the point of Washington, D.C. So the 0° latitude is at the equator. 90° latitude is about the North Pole or South Pole. Okay. So usually the North Pole or South Pole is added to the latitude. Okay. So to designate, okay, whether the point is in the northern hemisphere or southern hemisphere. Let us take the Washington, it is in the northern hemisphere. Okay. Northern hemisphere means above the equator. So it is called as a, so I'm putting as a 39° north. So it is in the northern hemisphere. And why I'm putting as a W? Because it is the western hemisphere. This is the east and this is going to be the west. So this N and W will indicate where is the location of my Washington. Okay. So the line drawn from the surface of the earth between the north is called as a meridian. A special meridian is called the prime meridian, is used as a reference point for measuring the longitude. If the line on the surface of the earth drawn between the north and south pole, then in process, okay, if you are drawing a line for the surface of the earth drawn between the north and south poles that passes through the Greenwich, which is in the England. So the longitude of the given point is the angle between the geocenter and content. So we are putting the east or west to designate whether it is located in the east or west of the pyramid. So the Washington DC, we can say that it is in the 39° of north and 77° of west, latitude and longitude. So this is what to show the latitude longitude for a satellite. Okay, this figure shows some kind of geosatellite where the satellite are fixed. Okay, the Earth is rotating. So it's not a circular, it's an elliptical orbit. We are fixing the satellite. So these satellites are called as the communication satellites. It's serving for the United States and some kind of countries in the North America. So this geosynchronous satellites, it will rotate about the equator. Their sub-satellite point is on the equator. Okay. So the geosynchronous satellites are the latitude of 0° because it is on the equator. So we can say that, this satellite is fixed at this particular point. Okay. Each and every satellite. Okay. So this satellite is having the coverage for the United States. This satellite is coverage for the Canada, kind of. So knowing the location of the satellites and sufficient information about the Earth stations, okay, that must communicate with the satellite. So the Earth station will rely on the azimuth angle and also the elevation settings of the antenna. So azimuth angle means it is a top angle at which it falls on the geocenter. We call that as an azimuth angle. And already we have discussed about what is meant with angle of elevation between the direction of antenna and between the ellipse. That's called the angle of elevation. So these two things are required, okay, to tell where to point the antenna, where to hit the satellite from the antenna. So the azimuth angle refers to the direction of the north pole equal to 0°. So it is measured the clockwise. Okay. So the angle of elevation, we have discussed that, it's pointing towards the antenna. So once you know these two angles, the Earth station antenna can be pointed to the direction. So the geo satellite, the antenna will simply remain in that position. That's all. The antenna will just to send and receive the signals. But whereas in the other satellites, we have to point to the satellite. For other satellite, the antenna must be moved as the satellite passes over it. Satellite is passing for other satellite, but we are talking about the comparison between your GEO and LEO. So for GEO satellites, the angles of azimuth and it's relatively easy to determine for GEO satellites because these satellites are fixed in position over the equator. So we have to use a special formulas, special techniques to permit for the determination of these angles at any point of the Earth. Now, the next one we are talking about on the satellite communication systems. Okay, so here in the satellite communication systems, the communication satellites are not originators. Okay, satellites, it is not the originators or it is not the source for the communication. So, but some satellites, they will generate the information like meteorological data, kind of, that has to be transmitted, and communication satellite do not. Okay. Communication satellite does not have any information within itself. Okay, so these satellites are relay stations. The source is only in the Earth. From the Earth, it goes to the satellite and again comes to the Earth. That's all. So the transmitting station cannot communicate directly with one or more receiving station. Okay. So we have to use the satellite. Okay. So a transmitting station, what it will do, it will send the information to the satellite. So from the satellite, it has receiving to the receiving station. So this satellite, which is used for this application, we call as a repeater. Okay, this is the normal basic diagram of a communication satellite. Okay, so this is a transmitting station. It transmits the information to the satellite. We call this uplink, which is about 6 GHz. And after the communication satellite, it receives the information. It resends the information. We call as a downlink. So where the uplink is about 6 GHz and downlink will be just 4 GHz. This is 6 and this is 4, and it is receiving to the down receiving station. Okay, so that is we can able to understand that satellite is one. What the work done by the satellite? It picks first one. It picks the signal, amplifies the signal, and it will translate the signal to another frequency. That is 6 to 4. That is the reason. These are the three works done by the satellite. So the signal of the new frequency, that's a 4, it will be retransmitted to the receiving station of the Earth. Okay, so we are having the uplink, means the signal transmitted to the Earth is called uplink, and the signal coming to the satellite is called as a downlink. So the uplink is 6 and downlink is 4. Okay, so this combination of the transmitter and the receiver we call as a transponder. The basic function of the transponder is two things. One is the amplification and to translate the frequency, because the downlink frequency to be lower. Okay, so the uplink frequency is higher, so it has converting the frequency, so it was going for the frequency conversion. So this is the repeaters and transponders. So it's a receiving antenna. First it will go for amplification. So it receives the frequency at the 6 GHz. We are having the mixer, so which is having the low oscillators, which generate the 2 GHz. Coming is to 6 and here is 2. And this mixer, what it will do, it makes a 6 minus 2, which is equal to 4. And then now the 6 is converted into 4. And now the 4 is again amplified and sends to the transmitting antenna. This is the way how the work goes on in your repeaters and transponders. Okay, so widespread transmit and receive frequency. That is, why we are having this particular frequency change. It will prevent the interference. Okay, so they also have some wide bandwidth unit, so they can receive and transmit more than one signal at the same time. So in the Earth station signal with the receiver's bandwidth will be amplified, translated to the different frequency. So the typical transponders have their own bandwidth. Okay, so to be economically feasible, we have to understand that the satellite must be capable of handling several channels. So most of the satellite consisting of many transponders, they're working with the different operating frequencies. For an example, communication channel can able to have a 24 channels. They polarize 12 vertical, 12. Okay, it's an example. Okay, so each transponders receives some individual channel. So multiple access schemes can be used to access the information from those multiple transactions. How to allocate the frequency? Okay, normally we know that most of the communication satellites, they operate in the microwave spectrum. Okay, so they work some work in different assumptions. Some work in a very high frequency, ultra high frequency. The amateur radio, they work with UHF or VHF. Okay, and then the microwave penetrate to the ionosphere, and then the low frequency signals also it can able to work. And this microwave spectrum is divided into frequency band, and then can be communication servers. We are also going to discuss about radar in the next class. Okay, so they can able to communicate with other services. And this is the band of frequency that is designated for the different frequency bands. So the satellite, we can able to understand which band, Ku-band or Ka-band, like that. So these are the typical bands what we normally use, the Ku-band and Ka-band. It means that the range of frequency by which these satellites operate for the satellite communication. So one of the widely used is called C-band. Okay, the C-band, we can, this is the most commonly used. Okay, because the people will ask, sir, why you are telling about the six uplink and the four downlink? It resembles your C-band. Okay, the C-band frequency is about 5.9 to 6.4. So we generally average six. The C-band, the downlink range is 3.7 to 4.2. So we are taking as a four. So you should understand that for a, while you're studying any engineering concepts, you have to know why we are using six, why we are using four. Blindly, you should not accept this point because we are considering a C-band satellite. So the C-band frequency, as per this particular table, it is given by this particular range. Okay, that is the frequency, the gigahertz, megahertz converted to gigahertz. So we can say that this is going to be the range. The average is going to be 6 and 4. So the C-band is given by 6/4. Okay. So over the past several years, the people are moving with this particular thing. Currently, they are using the Ku-band. Ku-band. Okay. The Ku-band means, the uplink is about 14 to, 14, and the downlink is going to be 12 gigahertz. And another one is called as a Ka-band. Okay. So most of the communication satellites now is operating the Ku-band. Okay. So because the C-band is quite overcrowded. Okay. So most communications are orbit now. So most of the things are operating the C-band. That is going by 6, coming by 4. 6/4. So there is some kind of difficulty with the interference because of heavy usage. Okay, so how to minimize the interference means, we have to future satellites, we have to convert to high frequencies. So naturally, the electronic equipment can able to achieve the higher frequencies quite complex. So the interference problems cannot be solved in other ways. So rather than that, we can go to change of bands like Ku-band, and the other bands are X band and L band. So the military people, they're using the X band for the satellites and radar, and L band is used for navigation because we cannot able to access this X band because X band is working with a different frequency. For communication purpose, we are using only the Ku band or C band. Okay, so X band is used by the satellites. And L band is used for navigation for the marine and aeronautical communication and also for radar. Spectrum usage, as I said, that the C-band is having its own uplink and downlink. Okay, so we can see the bandwidth between the upper and lower limits. Okay, so this bandwidth can able to tell you how much amount of signals you can able to carry. That's called the bandwidth. Okay, so for an example, for the lesser bandwidth, it can able to carry only less signals. For the more bandwidth, it can able to carry more number of signals. So 500 megahertz spectrum can able to go with a very low frequency through very high frequency. So most of the communication satellites is having the advantage of taking the full bandwidth. So it can able to carry the maximum possible number of communication channels. So wide bandwidth is one of the major reasons, where the microwave frequencies are so useful because it can able to take the multiple signals at the same time. We can able to, because it supports many channels, but also it supports very high speed data. So that's the reason that people now, they are working with the microwave frequencies for the communications. So the transponder, it receives the signals and picks the transmission there. The kind is channelized, and the 500 megahertz bandwidth, it's divided into 12 separate channels, and each and every channel is about 36 megahertz. So there are 4 megahertz guard bands. Okay, what is the reason for the guard bands? So the guard bands of the four, this is called as a guard band. It will prevent the signal associated with over here should not be transferred to here because this is the separate channel. Okay, so we can say that I'm having the complete frequency bandwidth of 500 megahertz. The 500 megahertz, I can say that is a starting frequency, and this is a ending frequency. If you're my 6425 minus 5925, which will be equal to 500 megahertz. So this 500 megahertz, I'm going to make it as a different channels, and each channel is about 36 megahertz. Okay, so the first channel, I can say that what is the range of the first channel, second channel, third channel, fourth channel. So all the channels are not connected together, and each and every channel is about 36 megahertz. And between the two channels, I'm keeping a guard band that is called the 4 megahertz. So whenever you're watching a television, you're having the multiple channels. So each and every channel, it is having this one frequency. So, and the another channel will have some kind of guard band. So note that the center frequency of the each channel. So we have to understand about the uplink frequency. And in the both cases, the 500 megahertz and the channel bandwidth are the same. So the transponders is allocated to 12 channels, and 36 megahertz, for the each and every channel is quite narrow when compared to the 500 megahertz. And each transponder is capable of carrying enormous amount of information. So one typical transponder can able to handle even up to 1,000 one-way analog telephone conversations, as well as one full color TV channel. So each transponder channel can also carry high-speed digital data. So using the various types of modulation, the 36 megahertz bandwidth can able to handle up to 60 Mbps. So the transponders are quite capable, so they can be overloaded with the traffic. So this more traffic that the transponders can able to handle. So they have developed so many techniques, to increase the bandwidth. Why they are increasing the bandwidth? Because to handle more number of information. Okay, and also the signal carrying capacity of the satellite. So two of the techniques, they use frequency reuse and spatial isolation. Okay, so just a minute, I can see how many students are. Okay, so today I can see only 33 students. Okay, fine. So one is called as a frequency reuse. Frequency reuse means, the doubling the bandwidth. If you double the bandwidth, what will happen? The information carrying capacity can be increased. Okay. And the communication satellite is provided the two identical sets of 12 transponders. The first channel in the one transponder is operating on same channel and the first channel and the other set and so on. So with this arrangement, the two set of transponders will transmit the same spectrum frequency and appears to interfere with each other. So this is not the case. So two systems, although operating on the same frequency, they are quite isolated. Okay, so this isolation is required to overcome the interference. So we may use a special antenna techniques that we normally call as a antenna polarizations. Okay, so the vertical polarized antenna will not respond to horizontal polarization. Okay, so that's the thing. So it avoids the signal, even though the bandwidth is there, antenna is there, but the signal will be designated to only then. It will avoid the interference. Or left-hand circularly polarized antenna will not respond to the right-hand polarized signal. So another technique is used to use the spatial isolation by using the narrow beam or spot beam antennas. The area on the Earth covered with satellite can be divided into smaller segments. So Earth station in each segments, they use the same frequency, but they use a narrow bandwidths of antennas. So no interference between other segments. This technique is called as a SDMA. So we all know about what is called a CDMA. Many people know the code division multiple access. Before it comes into picture, they are using about SDMA. That's called as a spatial division multiple access. So in that, it will give the access of the satellite will depends upon the location, not on the frequency. After that, to use the maximum available spectrum in the satellite, and also to ensure as many users as possible, the satellite will use some kind of multiplexing. Okay, we call as a frequency division multiple access. It was used in the early satellites. Today, they're using a TDMA, time division multiple access. Okay, so it's one of the digital technique, so where they will allow the time slot and the full bandwidth on the transformer. So the modulation methods like BPSK, okay, this is called the shift keying, band pass shift key, okay, quarter pole shift key. So and then amplitude modulation. So that 16 QAM, 32 QAM, 256 QAM is also help us to increase the digital transmission. So the spread spectrum is also used in the newer satellites. Now we are using the CDMA. Okay, this system, it will spread the signals to the multiple users over the full transponder channel bandwidth. Okay, and then it is used some kind of codes we normally call as a pseudo random codes. It uses pseudo random codes and then sorts the users, multiple users sorting, and it gives the priority for who. For an example, if 10 people are making a call at the same time, so depending upon the priority, it will connect the people the calls. That is called the CDMA. Even the mobile phones, we normally use a CDMA because it generates a random codes to make use of the to coverage for the multiple users. That is the reason, if one person is making a call, okay, one person is making a call, you're getting the another call which is on hold. It's all because of CDMA. If CDMA is not available, if one person is making a call, if another person is also making a call at the same time, you may not know that the other person is making a call. Now you can able to say that, if one person is making a call, the other person will be in the hold, or he will be in the waiting. How it is got? Because of this code division multiple access. It was initially what was used in the satellites. Okay, now we are using the multiple mobile phone also. It is about CDMA technology. So it is used in the wireless systems. Okay. And also it provides the security. So important. Okay. So, and also many satellites, they use the SDMA to give the multiple access. So that's all for the today class, students. Okay. So the today takeaway message of the today class is going to be, you have learned about the satellite. Okay. You learned about the basics of satellite. Okay. You learned about how to position the satellite. You know the difference between the LEO and MEO and GEO depending upon the position. You also understood about what is meant by synchronization between your satellite and the Earth surface. Okay. How to position the satellite, how to make the satellite kind of. So the next class, which is falls on our coming Friday, we are going to see the design of a satellite and what are the components available in the satellite. It's a very interesting. Don't miss that Friday class. I thought of taking by today itself, to complete that particular topic. But if I take so much of topic in the same class, you may forget some concepts. So a limited amount of information with maximum knowledge will help you to understand more about the satellites. So that's all for today, class students. We all are going to meet on the Friday, and this Friday we're going to have the design of satellites. So keep connecting with that particular thing. And if you have got any information about your final examination, please do share. I think by next week your exam starts, or the week later. I don't know that. So if anybody got the information, you please share. Okay. Thank you so much. God bless you all. Thank you all.
Thank you,
Thank
sir.
you, sir.